Hi everyone, I'm Dr. Kiran Raavi, working as an assistant professor in the Department of Electronics and Communication Engineering, MLR Institute of Technology, Hyderabad, India. So today we start Unit 4, that is about field effect transistors. So let us see the overview of today's presentation. So let us start with the introduction of field effect transistor. So we start with the basics of field effect transistor, and then followed by construction and operation of FET, and what is pinch off condition, pitch of voltage, then followed by volt ampere characteristics, and then voltage variable resistor. Conclude with summary. So let us see the introduction to the FET. So field effect transistor. Field effect transistor means here it is a 3-terminal 2-junction semiconductor device, just like a BJT. BJT, if you analyze a FET, if you want to analyze the FET, we have to compare this FET with BJT. So BJT is a current control device where output current depends controlled by the input current. So let us say, if you see the CE configuration, what is the output? Output current is IC, input current is IB. So output current controlled by the input current, output current IC controlled by input current IB. So therefore it is current control device, and whereas this FET is a voltage control device, because input gate current or gate voltage controls the output current, drain current. So let us see in detail. So it is also a 3-terminal. So what are the 3 terminals? Gate, drain, source are the 3 terminals of the FET, and it has a 2 PN junction semiconductor device, and it can also be used as a voltage control device, because I just now I told you BJT is a current control device, it is a voltage control device. The FET is a unipolar device. So another comparison with BJT. BJT is a bipolar junction transistor. Why the bipolar name comes from? Because the operation of BJT depends on both minority charge carriers and majority charge carriers. So hence it is bipolar junction transistor. Whereas in this case FET is a unipolar device, because the operation depends on either electrons or holes. If the operation of FET depends on electrons, then we can say it is N channel FET. If the operation depends on electrons, then we can say it is P channel holes, then we can say it is P channel conduction. So for FET, an electric field is established by charges present in it, which controls the conduction path of the output circuit without the need for direct contact between the controlling and controlled quantities. So here this is a virtual operation, you can say. For example, if you consider a magnet, so what is the magnet? Can attract some siblings, or we can say some iron material, small particles. So it can attract from nearby path, correct? So in such a way that means this is like a FET. FET can also be, the output current can also be controlled by the, which is gate current, gate voltage. So we can say it is the electric field. For the FET, the electric field is established by charges present in it, which controls the conduction path of the output circuit without need for direct contact between the controlling. So there is no contact between gate control and control quantities, even though we can able to control the output current, drain current. It has high input impedance. This is one of the important properties of field effect transistor. It has high input impedance and low output impedance, and it can be used as an amplifier and switch, same as like BJT. There are 3 types of FET. We have junction field effect transistor, MOSFET, metal oxide semiconductor, and it is again divided into 2: depletion mode MOSFET, enhancement mode MOSFET, and MESFET, metal semiconductor field effect transistor. So usually this MESFET is latest updated version of your FET, because in this we use gallium arsenide silicon transistor, which is having a high switching characteristics. So let us see one by one. We mostly concentrate on JFET. So we have N-channel JFET construction. So this is the construction. So coming to the construction, what mainly we required, if you want to construct N-channel JFET, we require an lightly doped N-type semiconducting bar like this. So which forms drain terminal and source terminal on either side of the N-channel. So it acts like an N-channel. The lightly doped N-type silicon or germaniums semiconducting bar. On either side of this, we have to diffuse heavily doped P-type semiconducting bars, and that forms gate terminal. Okay, so these are the three terminals. And now what are the two PN junction? This forms one PN junction and this forms one PN junction. So these are the two PN junction and three terminal device. What are the three terminals? Drain, gate, source. So there is no direct contact between drain and gate, but this voltage between this, the field generated by this VGS, gate to source voltage, can control the drain current, output drain current. So it's you can understand this operational construction of JFET by taking the analogy of this pivot tap, spigot, water spigot. So here source is tap, heavy water tank is there. So from this tank we can source, and then this water acts like electrons, and gate means this pivot. So from this is the drain. So by controlling this gate, we can control the water flow, right? So therefore we can further analyze this. It is mostly used, N-channel FET is mostly used nowadays, and a lightly doped N-type conductor silicon or germanium bar is taken that acts as a channel. A heavily doped P-type semiconducting material, that is silicon or germanium, is diffused on either side of the N-type bar. Electrons flow from source to drain like this. The electrons will flow from source to drain. So usually here the source is connected to negative of the battery and drain is connected to positive of the battery. So electron flow from source to drain, and output current ID flows from drain to source. This is ID current flow, which is opposite to the electron flow. So analogy is water spigot. So that is about N-channel JFET construction. Let us see the operation of N-channel JFET. N-channel JFET operation. So you can observe from this, here the drain is connected to positive of the battery. So this is variable. So we can vary this voltage VDD. So let us say VDD may be 1 volt, 2 volt, 3 volt, like that. So VDD means nothing but the voltage across channel. Across channel means drain to source voltage. So first case, when VGS is equals to 0 and VDS is some positive value. So if VDD means what? VDS may be 1 volt, 2 volt. So VDS is nothing but what? Drain to source voltage may be 1 volt, 2 volt, and so on. Okay. So this is the first operating condition, first case, when VGS is equal to 0. So already I told you that source is connected to negative here. So if you connect this gate and source, obviously VGS is equals to 0 volts, and we are giving some VDD. VDD means 1 volt, 2 volts, or 3 volts. So that is the VDD means voltage between drain and source. The depletion region between P gate and N channel increases as electrons from the N channel combine with holes from the P gate. So electrons combine with this. What happened? The depletion region increases. So these are the depletion regions on either side. So when we increase this voltage, the depletion region increases, okay, between the two PN junction, and that when combined with the holes from the P side. So because these are the electrons, right? So electrons moving from source to drain, and these are the P. So P p-type material having heavily doped and holes are present in this. So these holes are attracted these electrons. So we can say there is a depletion region, increase in the depletion region. So increasing the depletion region decreases the size of the channel. So size of the channel decreases means what? The resistance of the channel increases, which increases the resistance of the N channel. So even though N channel resistance is increasing, the ID current, drain current ID from the source to drain through the N channel is also increases. So you can say because there is a increase in the depletion region, so correspondingly decrease in the channel width. So when channel width increases means, channel width decreases means the resistance of the channel increases. When resistance of the channel increases, obviously current must be reduced. But it does not falls to zero because we are continuously giving the drain to source voltage. So therefore, it does not fall to zero, but it reaches some saturation level. This drain current will reaches some saturation level, and after that, the current is continuously constant. The drain current will be constant even you further increase the drain to source voltage. So we can say even though N channel resistance is increasing, the current ID, output current ID or drain current ID from source to drain through the N channel is increasing. This is because VDS is increasing. So we are increasing the VDS, right? So therefore, varying reverse bias potential across PN junction of an N channel is FET. So how we can represent this increase in the channel? You can say the resistance of the channel increases, right? So how we can analyze this kind of situation? So here we have applied 2 volts, and so this acts like a high resistance path, right? So there are combination of 4 series connection of 4 resistors, R1, R2, R3, R4, 4 resistors, let us say, and these 2 volts will be divided. So here at resistor 1, what will be the drop? So because 4 resistors are there, 2 volts is we are giving. So obviously 0.5 volts drop across this first resistor. All resistors are equal here. So here 0.5 drop will be across the resistor, first resistor. Then what will be the value at this point? At this point 1.5. So 2 volts minus 0.5, 1.5 volts available across the after first resistor. Then at this point second resistor, the voltage drop again 0.5 volts. So now it is decreased to 1 volt. Now again across this resistor next another 0.5 voltage drop. So that means 1 minus 0.5, 0.5 is the voltage here. Now across this resistor 0.5 minus 0.5, again 0.5 voltage drop. So finally you will get a 0 volts. So this way we can represent the resistance path of the channel. Now what is pinch off condition? So as we have discussed here, as we increase at a particular voltage of drain to source voltage, there is a chance the situation where both depletion regions touch each other. That means it pinches off the channel. These both depletion regions pinches off the channel. So in that case, the situation is called pinch off condition. What do you mean by pinch off condition? We can say 2 types. In 2 ways we can define this pinch off condition. So what are the consequences of the pinch off condition? So pinch off condition means where the 2 depletion regions touch each other, at the same time channel width is decreased and resistance of the channel increases. And one more important way to explain this is at that particular condition your VDS, the drain to source voltage, is exactly equal to VP, pinch off voltage. VDS is equals to VP, and in such case at this situation what happened to drain current? The drain current will be ID will be constant. ID equals to constant, and that is given by IDSS, saturated drain to source current when gate is 0, gate is shorted. So IDSS means what? Drain to source current, output current, drain to source current when your gate is short circuited. So here we can see if VGS is equal to 0 volts and VDS is further increased to a more positive voltage, then the depletion zone gets so large that it pinches off the N channel. Therefore, the channel width reduces. Channel width reduces means resistance increases and current will be decreases. But so we are continuing giving the VDS, drain to source voltage. So the drain current does not fall to 0. It will be maintained constant. This suggests that the current in the N channel ID would drop to 0 amperes, but it does not, just opposite. As VDS increases, so does ID also increases. So that is pinch off condition. And pinch off voltage, what pinch off voltage means? It is a voltage between drain to source at which two PN junctions or two depletion regions touch each other. And one more important way, what is pinch off voltage? The pinch off voltage is the voltage at which the drain current reaches saturation, that is IDSS. So it is a drain to source voltage at which both depletion regions touch each other, and we can say then VDS is equals to VP, and where ID reaches saturation. So here ID becomes saturated value, that is IDSS. So this way we can analyze pinch off condition. Now let us see the characteristics of the N channel JFET. N channel JFET characteristics. So this is the first case at the pinch off point. So here initially when you increase the VDS, initially there is a linear relation between VDS and ID. So VDS increases, ID also increases correspondingly. Up to what? Up to pinch off condition. When pinch off condition occurs, the current, ID current constant. ID current reaches saturation level when VGS is equal to 0 volts. Now at that point the corresponding drain to source voltage is nothing but VP, pinch off voltage. Okay. Any further increase in VGS does not produce any increase in ID. So, and VGS is at pinch off is denoted as VP. Now ID is saturation or maximum. So ID gets maximum value, that is IDSS. It is referred to as IDSS. The ohmic value of the channel is maximum. So ohmic value means resistance. This region is called ohmic region, right? So and IDSS is the maximum drain current for a JFET, and it is defined by the condition VGS is equal to 0 volts and VDS greater than VP. So after VP, that is pinch off voltage, the drain current is constant, right? So let us see the next one, N channel JFET operation continued. So second case, when VGS is equal to 0 volts, VDS is again some positive value here. So VGS is greater than 0 volts. So we should not write like this because it may be 1 volt, 2 volt or 3 volt VDS. For different, so by keep on increasing, the drain current also increases. Now what we have done, we have given gate to source voltage. So we have applied negative voltage. So we are increasing that. That means what? What happened? If you apply here negative voltage, we have connected P-type material here. Gate is connected to P-type. If you apply negative voltage, so negative is connected to P-type material, then we can say it is in the reverse bias condition. So the reverse bias condition formed when you apply negative voltage, negative gate voltage to the P-type current. Then we can say it is in the reverse bias. So reverse bias means what happened? So there is a increase in the depletion region in reverse bias. So obviously the depletion width will increase like this. Okay, but different values of drain to source, different values of this gate to source voltage, right? So when, for example, when gate to source, we know this one, when gate to source voltage is 0 volts, your characteristics will be like this. So up to pinch off voltage, there is a increase, linear increase in the drain current for the input value, that is output VDS. Now VGS is decreased to minus 1 volt. So now VGS is decreased to minus 1 volt. What happens now? So because we are increasing the reverse bias voltage here. When reverse bias voltage increases means the depletion region occurs early. That means the pinch off condition occurs early. The pinch off condition occurs for lower values of VDS. Here, see here. When VGS is equal to minus 1, so actually VGS is equal to 0, this is the pinch off condition. Now, when VGS is equal to minus 1 volt, this will be the pinch off condition. That means the pinch, now when we decrease the gate to source voltage, that is minus 1 volt, then the pinch off condition occurs early. Next, if you further decrease VGS to minus 2 volts, that means we are increasing the reverse bias voltage across this. When you increase reverse bias, so again the depletion region occurs early. The depletion width increases. The depletion width increases early and the pinch off condition occurs early for lower values of drain to source. So therefore, here it is decreased. This is the pinch off condition. Now, at a particular voltage of VGS, that is, if you further decrease the VGS value, so let us say minus 3 volts. So minus 3 volts, the drain current also decreases. So at a particular voltage, exactly at a minus 4 volts, you will get a drain current almost 0. However, it cannot be equals to 0. So there is a minute current flowing through the circuit. So right, that is due to minority charge carriers, right? So this is drain current. So this is the characteristics of your N-channel JFET when VGS is less than 0. So that means when we decrease gate to source voltage, the drain current also changes. That means so the output current, drain current controlled by gate to source voltage. So VGS is decreasing, the drain current also decreasing, right? Because we have increasing the reverse bias voltage. So when we increase the reverse bias voltage, the depletion region occurs early and correspondingly pinch off condition occurs for lower values of VDS. So this is about N-channel JFET operation when VGS is equals to 0 volts. Then let us see next case, FET as a voltage variable resistor. So this we'll see in the next session. Introduction. So what we have learned today, introduction to the field effect transistor, construction and operation of FET, pinch off voltage, voltage ampere characteristics, and then voltage. This will be discussed in the next topic. The next topic will be FET, applications of FET. Thank you.